This is the beginning of philosophy of thinking machines. And artificial intelligence is about emulating those thinking mechanisms. And probably you have heard of Turing test. So the Turing test is, there is a person sitting on the other side of the room. Can you hear me? So the person is sitting on the other side of the room, and the machine is on the other side, and in between there is an interrogator. And the task of interrogator is to know which response is coming from the machine and which response is coming from the human. If interrogator doesn't recognize which is machine and which is human, then machine is called to be intelligent machine. So how many of you think that ChatGPT has passed this test, or large language models have passed this Turing test? How many of you? Only a couple of hands. Hello. So actually in my class there is no gray level, so it's binary. So either you say yes or no. How many says yes? And how many says no? Still is gray level. I am coming from image processing background. I don't like gray levels. I need black and white. Threshold yourself. Again, how many of you think that large language models are intelligent according to Turing test? Okay, no more hands. Okay. But the catch in this paper, interrogator has to be expert, subject expert. So if let's say my mother says ChatGPT or this large language model, they are very intelligent. They can answer anything. But if I put something regarding to machine learning and ask large language models, sometimes they give rubbish answers. So within couple of minutes you understand that this is a machine. For me, still that large language models are not that intelligent to beat subject expert. So all of this domain started with the premise of creating something that we see over here. This is what is going around in our brain. This is neurons firing in response to some activity, some stimulus. And this firing makes neurons work together, which we call neural network. It is said if they fire together, wire together, they will be wired together. So this is the premise to create something like this using some mathematical models. If you know how many neurons do we have in our brain? Anyone? How many neurons do we carry? Anyone? Million, billion, trillion, quadrillion? How many? 100? 100 billion. And how many synaptic connections? Said trillion, but okay, there's one more thing. If you read some neuroscience literature, be careful, because neuroscientists say that we can answer your question with 10% probability. Okay? So this is a heads up, and I'm not exaggerating it. So the rough estimate is we have more than 10 trillion synaptic connections in our brain, and that is why we say that we are more intelligent zebrafish. Have you heard of what is zebrafish? Okay. The question is, are we more intelligent than zebrafish or not? We cannot say, because zebrafish has only 1 billion synaptic connections. We have more knowledge. We can store more knowledge, that is for sure. That is why we have bigger heads. That is the only thing we know with certainty. But are we more intelligent? Question mark. I am not sure. Okay, so the first breakthrough in the history of artificial intelligence. Have you heard of these two guys? Any one of you heard of these two guys? McClaw and Pitts. These are two neuroscientists, nothing to do with computer science. So when you have abstraction of the physical world using science, something big happens. And I will show you a couple of those breakthroughs when we consider how AI has evolved. So these two neuroscientists come up with the idea that, okay, we study neuron, we understand there is an axon, and if we combine electrical currents or in the vicinity of the neuron, if they are more than some threshold, they will fire. That is the only thing we know about neuron. So they come up with the abstraction of this using this kind of structure. Have you seen this kind of structure recently? So you have neuron. These weights are, by the way, synaptic connections. With the help of these weights, different neurons work together. Do we have AI students over here? Okay, so we have AI students. I got the answer from the, okay. Have you seen this kind of image before? This is 1943. And up till today, we are abstracting neuron approximately like this. So there is something like weights, there's an input, then we sum them together, and if they are more than some threshold, what is the threshold? In easy term, what is the threshold? Why we need to have a threshold? If I don't have a threshold, what will happen? Okay, she says something about limit. In 1943 article, they call this threshold as limiter. Thank you. This is called as a limiter. And why it is called limiter? Because we cannot deal with all the data. We need some zeros. If something is not big enough, I will suppress it. So right now, okay, one more question. Actually, I asked a lot of questions when I'm teaching. How many rods and cones or sensors do we have in our eye? Anyone? If you are looking at the image at the moment, how many sensors are getting simulated? Maybe in trillions. But how many neural connections are there from this eye or iris to the brain? Maybe some millions. So huge compression goes inside our brain. We cannot deal with all the data. And this is the premise of AI as well, because we are going to simulate what we have in our brain. So we need some kind of limiter, like divine power has given us this kind of limiter in our brains. We compress the data, right? Before I move forward, this is what we have. This is the latest neuron, or what we are dealing with these days. So again, we have some inputs, we have some unknown, which is written as theta. It could be anything. Any Greek letter would work over here. Then we sum them together, and then there's a function, which is a limiter. Now we call it as an activation function. That's all. That is the only difference we have made from 1943 till 2025. Exactly same thing. At that time, they were thinking about threshold. Now we have nonlinear threshold, some activation function. Okay, let's deep dive how actually neural network works. So if you have data from two different classes, maybe they are malignant or benign cells. I work with medical imaging, so we have that kind of a data. And what neuron will give us? A line. That's it. A linear surface. Maybe it's, if you know equation of line, it is mx plus c or ax plus b, whatever you want to call it. It's w1, x1, w2, x2, where it's the linear surface at the end. Okay, it's not a line, it's a plane. Okay, it's not a plane, it's a hyperplane. Because we don't have nouns for all the dimensions. We call it hyperplane. But at the end of the day, we have a linear surface that separates the data into classes. But again, then you say that there is some misclassification, right? In some green circles, I have red cross. How to deal with that? What we can do? So what line does, if you know mathematics, all the samples that lie on one side of the plane, they will give me some positive output for that equation, and all the samples on the other side will give me some negative value. And that is the classification. I just need to classify the data. So I have infinite number of decision boundaries, right? This could be decision boundary, another one, another one. But the real intelligence comes when you find the decision boundary, but not a decision boundary. The means the perfect to the level we can get. Right? So all the intelligence comes how you find these weights. Because I have this control, this is synaptic connection in our brain. This is how our brain works. When a lot of neurons fire together, we wire them together. I will talk about it. It is called synaptic plasticity. So all the intelligence comes down to the fact how to learn those weights to have that linear surface that classifies the data. So one of the earliest learning rule in neural networks was proposed by Donald Hebb. It is called Hebbian rule. Have you heard of that Hebbian rule before? Again, a neuroscientist. The core idea is often summarized as neurons that fire together, wire together. Fire together, wire together means if they are working together, if they respond to a stimuli in the same manner, we should make a network out of it. This is how brain is getting trained. This is how kid learns to talk. This is how kid learns to balance themselves. So there is a neural network. And I was asking how many neurons do we have in our brain? When we were like 2 years, 3 years, we have maybe 2 times more neurons in our brain. But as we get old, these neurons die because we were not using them. So this is the natural process of decaying of neuron as well. As an adult, we actually have half of the neuron as compared to once we were born. That is why it is easier for kids to learn a new skill because they have more neurons at that time. So if they start learning some new skill, they will train the network and they will retain the neurons for the rest of their life. Okay, coming back to Hebbian rule. If 2 neurons, say A and B, are active at the same time in response to some activity, okay, this is okay. I will use very few mathematical notations because I want to go through all the core ideas. But this equation is the core. This is Hebbian learning rule 1949. It says that some eta, now we call it learning rate, xi and xj. Xi is presynaptic connection, xj is postsynaptic connection. Pre means a neuron that is before the neuron that is trying to learn a weight, and post is afterwards. So if the neurons are working together, weight will go high. And eta, if eta is 0, it means we are learning nothing. If eta is 1, it means we completely trust our sensations. But this is not true as well. So eta is usually 0.2, 0.3. From the very beginning of AI, scientists came to the conclusion that this learning rate would be around 0.2, 0.3 because we cannot trust our sensations completely. And if eta goes to 0, we'll not learn nothing. So this is the collective wisdom of all the scientists from the very beginning. Then comes delta rule. Anyone heard of this delta rule? Anyone have seen this equation like this before? Very familiar equation if you are into AI or deep learning or computer vision. It says that everyone understand what is weight? Why I am trying to convince you that weight is important? Because this is how neural network is getting trained. If I move weight, it means the network, the neurons are closely connected. They are working together. If weight is light, it means synaptic connection is loose, right? So we are trying to learn this weight. And D is desired output, and Y is what neuron is giving me. Okay, have you seen this equation before? Have you heard of gradient descent before? Any one of you heard of gradient descent? Does this equation look like gradient descent? Nashta nahi kiya. Have you had breakfast? You had breakfast, okay. Is this look like a gradient descent? This looks like, to me it looks like a gradient descent, but it's a delta rule. Now we are not calling it gradient descent. We'll talk about gradient descent. Okay, moving forward. Then came the biggest breakthrough in 1950. This is 1958. This is Perceptron. Then came this guy, Frank Rosenblatt, working for US Navy. So he was working for, this is Cold War era. Consider the fact we are in Cold War era. So there were a lot of money was pumped into defense projects by US Army. Before I talk about it, just read what I have highlighted. It says that neuron, they expect, will be able to walk, talk, see, write, reproduce itself, and be conscious of its existence. This is the height of exaggeration I can read in any literature. Even after 70 years, we are not able to achieve all the tasks. But just this guy proposed Perceptron, which is a linear classifier, I will explain. It just draws a line between data samples, but this is what the news clipping says. This is exactly the same what you see in media today. जब वो flash होता है ना, breaking news. So this was a breaking news in 1959, and press clipping says that they have found the way a machine will reproduce itself, it will be conscious of its existence, it can walk, talk, and see. This is height of exaggeration. But what exactly was Perceptron was this. Again, this Perceptron looks like what we have seen before, 1943. Exactly same. But the good thing now, we have the learning algorithm. Before that, it was the abstraction that how neuron will work. But why Perceptron is famous? Why Frank Rosenblatt is famous? Because he gave that learning rule, like how this neuron will be trained. This was the new thing. There is nothing new. Perceptron learning rules look like exactly delta rule. So these are jigsaw puzzles. Some guy found something, and after a couple of years, another scientist found that, okay, this is an interesting idea, I can use it. Right? This is how science progress. So this is 1958, 59, Perceptron. And still we are using same Perceptron. You work in neural networks, this deep learning. This is the basic building block. The only difference is that function, जो f वहाँ पे लिखा. At that time, we were talking about threshold. Now we have multiple activation functions because we know that we are working with deep learning. There's a problem of vanishing gradient, exploding gradient. We cannot have threshold. So better ways to do it. But the abstraction remains exactly same. Then this came, this gradient descent. But gradient descent actually was much older. Have you heard of the name Cauchy? Famous mathematician? Cauchy-Schwarz inequality, if you have done linear algebra course. I'm not sure, but have you heard of this? Okay, perfect. So this method of gradient descent is much older, proposed in 1947 for mathematical optimization. At that time, there was no concept of perceptron, learning rule, or anything. It was mathematical optimization. If you want to find maxima or minima of function, you take negative of the gradient. That we know from 1847. But this Arthur Samuel, this guy, he built a system that used gradient-like learning algorithm. So the idea came, okay, that learning can be done using mathematical optimization. Maybe it's much better. So this was the idea of gradient descent. So if you are walking on this surface, this is a search space in which your solution lies. Or in simpler terms, this is surface of cost function. And if you want to minimize the cost, you walk against the gradient to reach global minima or global maxima. It's up to you, it's your definition. So this gradient descent was proposed in 1847. In 1960s, scientists rediscovered it, okay, that we can use the same idea to go down the hill to find the function minima, because this is like going down the hill, right? Then, actually, this is we called AI winter. I'm not going to go into detail because of time constraint, but this actually, when Perceptron was proposed, it was the hype that it can walk, talk, see, a lot of other things. But then the book was published named Perceptron, which proved that Perceptron is only a linear classifier, and it even cannot learn XOR data or exclusive OR data, because that is non-linear, only 4 data points. So that was the beginning of AI winter. But at the same time, we have something called multi-layer perceptron, exactly what we have as a deep learning architecture these days. But funding was dried down. It's AI winter time. No one was talking about AI. But scientists have a very different view. They say, okay, we'll not do AI, we'll do machine learning. We can talk offline, what is the difference between AI and ML? But scientists say, okay, we'll stop doing AI. Now we'll work on ML. Okay. I'll just catch my air, not like this, but like this. But this is multi-layer perceptron. Okay, same perceptrons, but if you want to have a non-linear surface, okay, I can have multiple perceptrons working together, like how it is done in our brain. Then we could have a non-linear surface. Simple idea. Okay, without this guy, we cannot have deep learning like we have today. This guy is Paul Verbos, 1974, MIT, not Stanford, I guess, Stanford PhD. He proposed backpropagation. Okay, we found gradient descent, but how to use it to train multi-layer perceptron? No one knew. No one knew. It was okay for a single neuron, but if you have 10,000 neurons, what we can do? So this guy came with his PhD thesis, and he said, okay, I don't know how to do it exactly, but I know that you have to put the error back into the network. That was his whole idea of PhD, that to train a deep learning network, calculate the error at the end, because this is a feed-forward network, multi-layer perceptron. Once you have the error, put it back in the network and learn something. He didn't give example. And that is why people forgot about his invention. He proposed that in 1974, and then he was rediscovered in 86 by Jeff Hinton, the same guy who got Nobel Prize of Physics, but he's a computer scientist, in 2024. Right? So backpropagation, critics argued and still do that backprop doesn't resemble how real brain work. Okay. We are moving away from neuroscience-centered AI to mathematical optimization. Now mathematics is overtaking the whole field of AI. And Paul Verbos didn't have practical neural network training, which was done in 86 later on. So the AI community didn't immediately recognize the value. This is, again, something that science has seen many times. If you read history of science, something is discovered, but no one gives importance to that invention. And maybe after 50 years, 70 years, 100 years, someone rediscovered it and said, okay, we can use the same idea somewhere in the other side of the globe. They have different ideas. So this is one of those cases. Backpropagation is backbone of deep learning. Without it, there wouldn't be no deep neural network powering today's AI. Consider the fact. Without this, we will not have any AI that you are using these days. Coming to 1980s. Okay, we have some neural network, but the problem was what to give to the neural network. People were talking about, okay, I'll have the handcrafted features. I will take the data from the skin and I will tell, okay, this is the color histogram of the skin, this is mean value, this is standard deviation. But the problem is, are you sure? Do we really need to have this kind of data? But we don't have deep learning at that time. And this whole idea of handcrafted features, I'm merging computer vision a bit over here because they overlap. In 1959, Hubel and Wiesel did an experiment, and these two scientists got Nobel Prize in Physiology in 1980s for this study. They put electrodes in the brain of a cat and showed different stimuli, if you can see in the image. And they found that our brain has S cells and C cells. So they respond differently to different orientations of the edges. So they came with the idea that we need hierarchical learning. So this is some kind of hierarchy. And this idea was then captured by a scientist called Fukushima, and the invention was new cognitron. This is 1980. Does it look like convolutional neural network? Exactly same thing, same layers. Convolution pooling, convolution pooling. But this was motivated by the study of Hubel and Wiesel, because they give this idea that we have convolution, our brain reacts to this different orientation, different way, and then on top of each other, they combine all of those stimuli. By 1980, convolution neural network, no one knew before 2010, right? So again, one invention that was not used at that time. I have been told that I have only 2 minutes left, so I'll be quick. You can talk to me offline if you're interested in that. But impact of new cognitron, this picture on the left is AlexNet, beginning of deep learning. If you know what is ImageNet, this is the champion network, 2012. Exactly same as new cognitron. The only problem at new cognitron was there was no learning algorithm. They didn't know about backpropagation algorithm. But they had the idea in their mind, and that was captured later on. I'm skipping that. I have to, yes. This idea was captured by this guy, Jean LeCun, convolution neural network. Everyone knows who is Jean LeCun? Chief scientist of Meta, a French guy. Okay, in 1989, he took the idea of new cognitron, combined it with error backpropagation, and voila, he has the network working for hand character recognition. It was a big hit at that time. At that time, SVM was also there. I'm not talking about SVM because I was just focusing on deep learning at the moment, but this is the same era when SVM was rediscovered. Have you heard of support vector machines before? Support vector machines were 1960s, rediscovered in 1990, till the guy moved from Russia to USA, to Bell Labs. When he published his article in Russian, no one gave importance. Same idea, 1990, everyone said, oh, wow, it's better than neural networks. Okay. This is how science progresses. Okay, I'm just skipping that. This is something no one talks about much, but I guess without this restricted Boltzmann machine, we will not be able to train deep network. Because in 2006, Jeff Hinton showed that using, Jeff Hinton showed that we can use deep learning not only to classify, but to generate data. Beginning of generative AI, beginning of LLMs. Before that, no one knew, okay, can we learn probability distribution as a function now? Can we do that? No one has this idea. 2006, Jeff Hinton gave this idea, yes, you can do that, using restricted Boltzmann machine. Restricted Boltzmann machine is exactly like how our brain works. It's not feed-forward. We have a 3D structure. We don't know where is an input, where is an output. We have multiple inputs, multiple outputs. How to train that? No one knew. And this is the beginning of autoencoders as well. RBMs are predecessor of autoencoders, and then GAN or GANs. Okay, I'm skipping autoencoder. AlexNet, that is the slide I showed you earlier. ImageNet is a challenge that has 1 million images around of, I think, around 1,000 categories. Because of this one challenge, we have AlexNet, VGG, GoogleNet, ResNet, DenseNet. All of these, I think, most of you has used or have studied. Maybe some has published something using those networks. These are all because ImageNet challenge. They were all proposed for ImageNet challenge. Beginning of generative adversarial networks. Ian Goodfellow. He wrote this book of deep learning. If you are a student of deep learning, probably this is the first book we recommend to have. Okay, I'm just skipping that, I think. Okay, can you recognize these faces are real or fake? These are all fake faces, by the way. These are all fake faces generated using generative adversarial network. And predecessor was autoencoder. Before that, there was restricted Boltzmann machine. Before that, there was backpropagation. These are all pieces of jigsaw puzzle. If you don't understand this puzzle, you will not understand where we are and how we have reached here. Okay, last but not the least, I have skipped LSTM, I have skipped RNN, because with transformers, with large language models, we are not talking about RNNs anymore. But what transformers has done, that now we know how to encode long-term dependencies. If you have 10,000 pages digest or a novel, and in the last page it says, and then they found that Jim is the murderer. What is meant by they? Can you infer back? Because they was given their definition of they was like 10,000 pages before. How to encode that? Transformer has this ability because it overcomes decaying gradient or vanishing gradients. If you have vanishing gradient problem, only couple of layers will be trained, and all the layers before that will not be trained. So transformer has this idea. Transformers are large-scale correlation matrices, value key, you know. So, if you talk to me in terms of mathematics, they are like gigantic matrices with lot of correlations going on. That's all transformers do, with lot of fancy words. Okay, vanishing gradient. Okay, I'm just skipping that because I overstepped the time. I think this is the most important slide. Where we are heading. So we started with Turing paper. We have I haven't talked about information theory, but without information theory, we will not have entropy. We don't have information gain. We don't have KL divergence, which is the basis of GAN again. Then we have first AI winter. After Perceptron, as I told, because Perceptron cannot learn more than a linear surface. 80s was expert system, but later realized that probably they are not fulfilling the promise it has. Second AI winter came. And then revival was restricted Boltzmann machine or deep belief network. Without that, we will not reach a point where we are. 2012, beginning of convolution neural network. Big revolution. But this is based on new cognitron, 2012. 2017, transformers. I'm not sure where we are heading, but the problem I see is AI community is promising a lot without considering the ethical implications, the impact it will have. I'm not sure we are heading towards third AI winter, because we will not have winters like we have before, because AI is part of our life. But where we are heading is a question mark, because we could have a lot of implications and we are not mitigating all of those concerns and the problems of AI. So this is where research lies, where we need to put efforts on, and probably this is the area open for research. Okay, thank you very much. Thank you. Do we have time for a question?
Thank you so much, Dr. Khan, for that illuminating perspective on where artificial intelligence has come from and where it's headed. So our next keynote is by Professor Dr. Hussain Arsalan, Dean of Engineering, Istanbul Medipol University, a leader in physical Mac research, and IEEE fellow. Professor Arsalan is internationally recognized for pioneering cognitive radio technologies and charting the path from 5G to 6G, highlighting new advances in IoT and smart connected systems. His talk is titled, "Are we ready for 6G vision? What's next? Flexible and cognitive radio access technologies for 5G and beyond." So let's warmly welcome Professor Dr. Hussain Arsalan.
Okay, Bismillahirrahmanirrahim. First of all, I'd like to thank the organizers and the leaders of the Bahria University for the invitation. It's an honor to be here. This is my second time in the Bahria University, and I'm hoping that I will come over and over again in the near future, and hopefully will be collaborating with some of the faculty members here in the Bahria University. So, also, I would like to thank Dr. Rizwan for the great presentation. And I don't know whether, a presentation after his presentation is going to be interesting to listen, but I'll try my best. So my talk is going to be on communications, wireless communications.